Hello all, this is Rohit and today we are going to talk about additive manufacturing. So additive manufacturing is a process of creating an object by building it one layer at a time. So it is opposite to subtractive manufacturing in which an object is created by cutting a solid block of material until the final product is complete. So basically it's opposite to the traditional way of manufacturing. If you can see an example of some sculptures and all. So in earlier times they used to take a big chunk of some rock or something and then they just used to cover the original structure from that. So it's opposite to the subtractive manufacturing. So technically additive manufacturing can refers to any process where a product is created by building something up such as molding, but it typically refers to 3D printing. So it was first developed prototypes in 1980s. These objects were not usually functional. This process was known as rapid prototyping because it allowed people to create a scale model of the final object quickly without the typical setup process and the it and cost involved in creating a prototype. They were basically high. So as additive manufacturing improved, its uses expanded to rapid tooling, which was used to create more molds for final products. By the early 2000s, additive manufacturing was being used to create functional products. More recently, companies like Boeing and GE have begun using additive manufacturing as integral parts of their business processes. So additive manufacturing is also known as 3D printing. So we'll just quickly discuss how it works. To create an object using additive manufacturing, someone must you first create a design. So design is very important. This is typically done using computer-aided design CAD software or by taking a scan of the object someone wants to print. So software then translates the design into layer by layer framework for the additive manufacturing machine to follow. This is sent to the 3D printer, which begins creating the object immediately. So now I'll just share my screen, a small presentation. So I hope the screen is visible. So first we'll talk about the concept. So additive manufacturing technologies that build 3D objects by adding layer upon layer of material. The materials which are used are plastic, metal and concrete, etc. Complement to foundational subtractive manufacturing as we have discussed like forging, drilling, etc. And it is also known as 3D printing. So additive manufacturing, there are basic three important components of this. First is the 3D modeling software, as I already discussed, the CAD software, the machine equipment, and the layering material. Talking about the history, as we have discussed that in early 1980s, the prototypes were being developed. So 1981, the first solid printed model built up in the layers using photopolymers. 1984, Charles Hull invented stereolithography. 92, the first stereolithographic apparatus SLA machine created. 92, the same year, the first selective laser printing stirring SLS machine was created. Now 1990 to 2010 is known as the adolescent period. In 99, first ever 3D printed organ implanted in human. And 02, 3D printing met the open source movement. And 06, commercial availability of SLS machine. In 2008, Darwin self-replicating 3D printer that could basically build by itself was created. Now, present scenario is 3D printed aircraft, as I already mentioned, that Boeing and GE, they are very well using this technology. So 3D printed aircraft car body, smart robotic arms are being created, and bone replacements is also used in the pharma industry. Benefits of additive manufacturing. So design driven manufacturing process where design determines production and not the other way around. So it allows highly complex structures which can be easily extremely light and stable. Provides high degree of freedom, design freedom, optimization and integration of functional features. Manufacturing of small batch sizes at very reasonable unit cost. Talking about the process, CAD is very important, used to design producing a digital model. Design considerations play a very crucial role in additive manufacturing or 3D printing. STL and file manipulation. So conversion of CAD file to stereolithographic file using triangles polygons to describe the surfaces of the object. So STL file is taken to the slicer program, then it converts to the G code. Continuing, so printing, the machine follows an automated printing process run by the pre-installed software, which is followed by a layer-by-layer printing approach. 3D printing machines use intricate parts, so high maintenance and calibration is required for perfect prints. Removal of prints, so depending on the industry and the type of product, this can both be simple as well as complicated one. Controlled environments and highly skilled personnel are required to separate the printed part from the build platform. Post-processing vary as the printer technology. STL requires components to be curved, cured under the UV radiation before handling. Metal parts need to stress relieved in ovens. FDM can be handled straight away. Post-processing techniques involves tumbling, high pressure cleansing, polishing, and coloring to prepare the print for end use. Now, talking about the sectors where this printing is being used. So, firstly, aerospace industry, because it's an industry where things should be stable, things should be reliable. At the same time, they should be light in weight. So, aerospace industry is the perfect industry for this 3D printing technique. So, aerospace industry was first among one to go for additive manufacturing. Follows some of the very toughest industry performance standards that exist in the zone. Some common applications include environmental control system, ECS ducting, rocket engine components, combustor liners, oil and fuel tanks. Consumption of comparatively less material with consolidated design results in overall weight reduction. So weight is a very important factor in aerospace industry. So 3D printing is very good technology which is being leveraged by the aerospace industry at a very large scale. Companies like Boeing are very highly active in this arena of 3D manufacturing. Medical science, medical manufacturers are utilizing wide range of high strength and biocompatible 3D printing materials. Some major applications shaking up the medical industry are the orthopedic implant devices, dental devices, etc. Direct manufacturing, Stratasys Direct Manufacturing continues to expand its offering to support medical applications such as seamless medical cards, anatomical models, and some custom surgical tools. Transportation industry. So the transportation industry needs components that stand up to harsh testing and are lightweight enough to avoid or negate any unnecessary drag. Additive manufacturing helped automotive suppliers and companies to develop consolidated lightweight components that can lead to more efficient vehicles. In the energy sector, the 3D printing advancements in producing on-demand, efficient, lightweight components and environmentally friendly materials provides the answers for diverse requirements for and field functions. Key applications have merged from the gas, oil, and energy industries, include rotors down to whole tool components and models, flow meter parts. It is also widely used in the consumer products industry. So 3D printing helps to develop iterations and quickly adjust the design. Other successful applications include entertainment props and costumes, lightweight models and sets, and finely detailed architectural models. Now we'll take some examples. So first we'll talk about the GE General Electric's journey about with additive manufacturing. So there are three levels of thinking about additive manufacturing at an industrial level. Level one, first is the component thinking. The well-known CFM LEAP 1A fuel nozzle is classed as level 1 additive thinking. In this case, additive manufacturing was applied to an existing multi-piece part, reducing the number of components from 20 to a single piece. So one particularly costly process that was eliminated by the move to 3D printing was that a nickel alloy braced together with foils using gold in traditional nozzle method is no longer required. Level 2 is the systems thinking. Level 2 systems thinking is evident in the CT7 combustor. This was an 18-month project of an engine that powers fixed wing craft and helicopters. On the combustor, the fuel nozzles plug into top, and by using the 3D printing, over 100 pieces were consolidated into one. So basically, it was helping them to reduce the cost by eliminating the unnecessary pieces. The redesigned systems gave significantly cooler metal temperature. So this parameter was also taken care of. Level 3, tearing down the product and designing for additive manufacturing, DFAM. Today, GE are at level 3 or at DFAM. In advanced turboprop engine, ATP, Application of additive manufacturing, 855 parts were reduced to just 12 parts. So it was also very great achievement by the GE. So 855 parts were directly reduced to 12, and the new process eliminated all structural castings, although some castings is still required. The ATP has 20% lower emission fuel burn, 5% weight reduction, and the test schedule reduced from 12 to 6 months. So time was saved, the weight was managed, and the cost was ultimately the major factor which plays a great role in every industry. So additive manufacturing helps in all the things to balance out all the parameters. Now we'll talk about Boeing. So applying additive manufacturing in integrated mechanical design. The first significant application of additive manufacturing in this area of Boeing was to the SES-15 spacecraft. The team identified several areas of opportunity, including a new design for a nadir surface mounted optical bench. This architecture required a systems approach which not only addressed additive manufacturing but also the way that the additively manufactured components would function in an integrated assembly. So additive manufacturing alone did not offer significant technical advantages, but at this, when applied in a concert with new composite and adhesive materials, yielded a lightweight, low-cost, thermally stable design solution, which is the major thing in the aerospace industry. SES-15 project was used to establish the acceptance test regime that is now applied to all flight hardware that is 3D printed within the Boeing space and the missile systems organization. As production has been deployed, cost and cycle time data have been collected and reflected back into the future part selection decisions. With three different material systems at TRL-9 and an expanding supply base, additive manufacturing is now being actively traded applied to flight systems. Now we'll talk about some case study, GE and Morris technology. So in 2002, GE Aviation bought AM Morris Technologies as one of the biggest metal additive manufacturers in the world. The conventional method involved making 20 separate parts and welding them together it was a very highly labor intensive process. Now, additive manufacturing allows the production of pre-assembled nozzles. They aim at making 10 to 20 fuel nozzles for each engine, 20,000, 25,000 nozzles a year. So 50% of jet engines will be manufactured using AM in the near future. Case study 2 is of Rolls-Royce. So embarking on the journey of additive manufacturing of the entire components of this premium brand results in the faster production and lowered cost. Initially takes 40 to 60 weeks to manufacture a component while AM can complete the same process in about a month. Improved buy to fly ratio on materials. Figure for components machined away high has greatly reduced. Main advantages are economic viability and the processes will be as reliable and robust as traditional methods. Now, what is the potential of this AM additive manufacturing in the near future? So, industrial application, aerospace, automotive, medical sector, etc. It's basically everywhere nowadays. Impact on future manufacturing as a replacement of existing production methods on their substitutes. Growth and global value, rapid and substantial $10 billion by 2021. Metal additive manufacturing machines offers new possibilities not only in design but also in choice of materials like titanium, where the conventional processes can be expensive. Potential application, manufacturing components for transportation using lightweight engineering for better mass distribution. Ability to manufacture customized products as demonstrated in medical and orthodontic sensors. Now we'll talk about the challenges. So challenges that must be addressed can include financial considerations. Yes, finance is always the major thing, which has a highest impact, I should say, in each and every technology or something which is to be adapted. So financial considerations, capital expenditures for machines and facilities necessary to support additive manufacturing are considerable. So at present, because it's not a very leveraged manufacturing thing, so technology, so initial on the in the initial stage the application cost will be, yes, much higher, but in the long term when the cycle will get started, then the total expenditure and the total cost will be reduced. Certification and regulation. So the technology to assess the safety, quality, and reliability of additive manufactured parts lacks the design and manufacture technology, limiting its use to be broadly accepted. Yes, so the safety is also a major concern. Repeatability, while manufacturing flexibility is an asset, ability to create reliable parts on a consistent basis is challenging. So the cycle has to start. So overall the cost will be reduced. At the same time, when the production is started and the technology is widely accepted, more research is being made. So ultimately, with the repeatability of the things, so ultimately the parts will get manufactured, more safety norms will be there which will be followed, more technical trainings will be there. So over a period of time when the technology will be widely used, so ultimately these all challenges will be catered. It all faces speed of production challenges which limits mass production potential. A skill gap, a well-trained, capable, skilled workforce is a significant barrier. So it will be catered with time. So this was all about the additive manufacturing from my side. You can post your comments and suggestions in the comment box below. Thank you so much.